On behalf of Rigaku, welcome to everybody to our webinar on the analysis of alternative fuels using X-ray fluorescence. Our presenter today is Carmen Kaiser-Brückmann, and my name is Niels Heppe. I'm hosting this webinar today. Just a very brief introduction to myself. I'm a chemical engineer and have a PhD in chemistry. And before joining the XRF application team here at Rigaku, I worked in academia and was focusing on analyzing electrode materials with various kinds of spectroscopy solutions, including X-ray fluorescence spectroscopy. Before we start, let me start with a little bit of organizatory things. We would like to answer your questions at the end of the webinar. We intend to answer all your questions. We will select a few to answer here live in the webinar, and every other question is answered afterwards via email. Please place your questions not in the chat directly, but in the Q&A section. Yeah, and then we will we'll start with the introduction of my colleague Carmen Kaiser-Brückmann. She's also an XRF specialist here at Rigaku. We are supporting the EMEA region, so Europe, Middle East, and Africa, with application support for XRF. This includes demos, trainings, and method development for our customers. Before Carmen joined Rigaku, she has an extensive record in the cement industry, managing several analytical labs for different companies, and have a great proficiency in XRF. And yeah, with this, Carmen, would you like to take over and tell us a little bit more about alternative fuels?
Yes, I would love to. Thank you so much, Niels, and we'll chat later for the question and answer. Okay. All right. So thank you for joining, and we would love to present to you the overview of the webinar. So the webinar will encompass the changes in the cement industry. So there's a huge change, and this is why we would like to talk about alternative fuels. And of course, what the important variables will be that will influence the clinker burning process when we use alternative fuels. So we will look at what the influence is of the alternative fuels. But of course, the process, people need to get quality results from a laboratory. So I will show you how to analyze these alternative fuels using wavelength-dispersive X-ray fluorescence. And one of the methods that we will show is how we can use a scattering FP method for the quantification because it's complicated materials, a complicated matrix, and very heterogeneous. So we will also look at how we can prepare the samples. And then lastly, we will end off with the Rigaku WDXRF solutions and how Rigaku can provide the service and support that's needed. And then we will summarize and conclude with a question and answer session. So today I'm going to show you very unique XRF applications in the cement industry. So traditionally, an XRF spectrometer is used for quality control of all the raw material that we need to use in the process. And then, of course, as you can see in this diagram here, I just get my pointer. Yeah, sorry. Yes, you can see that the XRF is really used from mining, crushing, pre-blending, raw meal analysis, kiln feed analysis, clinker analysis for the storage, the cement grinding and the cement storage and packaging and distribution. So at this whole process, we will use the XRF spectrometer, but we are going to focus on the burning process. So how we can use the XRF to measure these alternative fuels. So, of course, what are basically the coming changes in the cement industry? We need to ensure that we have a stronger requirement for a better thermal and energy efficiency, yes. So therefore, we try to use more alternative fuels, and we can increase clinker substitution. Yes, very often there's a shortage of skilled personnel due to a variety of factors, of course, and there's always a huge cost pressure in all parts of the process. So all of these points that I've spoken about are basically the new requirements that we need in a modern cement plant. So, of course, laboratory control needs to maintain the performance, even when we have difficult materials like alternative fuels. So in the past, it was very easy to measure the standard materials, but now it's becoming increasingly difficult. So we still need to provide the excellent analytical results for the current and the future plants that will be present. So, of course, all of this will have an excellent return on investment, and we will have a lower cost of ownership over a very long period of time. So if you look at the traditional clinker burning through the ages, we started in 1824, where, of course, the Portland cement was invented, by burning like chalk, and finally divided this clay in a lime kiln, yes. And as you can see, this is the timeline. So in 1845, we had the raw materials of Portland cement clinkering temperatures. In 1849, we did the first accurate chemical analysis of Portland cement by wet chemistry. Yes. Then, of course, in the 1860s, we began the era of Portland cement composition. In 1886, it was the first rotary kiln that was produced and introduced in England to replace the vertical shaft. And then in the 1909, we issued the patent for the rotary kiln. So it's a very long history of this clinker burning process. So a clinker composition consists of the main elements that here we can see. So in the cement world, we call the calcium oxide with a C, the silicon dioxide with an S, the alumina with an A, and the F with a which is the ferrate. So we need these compositions in the clinker, These are the main elements. So I'm showing you this because these elements will be influenced by the analysis, by the burning of the alternative fuels in the process. So, of course, the end product will be used, of course, to make the cement. But if you look at this diagram, you can see that we have the kiln here, we have the fuel, we have the raw materials. So, of course, today we will look at the fuel, how this composition will influence this end product, which will be the clinker. So if we look at the kiln, the geometry, the speed and the slope will influence this. The preheater and configuration will influence this. And the cooling characteristics will influence this. Of course, the raw materials, the mineralogical composition is important. The particle size distribution is important. The degree of calcination, and of course, the thermal history. So if we look now at the fuel, when we use the fuel in our kiln, as you saw in the process, we will have an ash, and this composition of the ash will add to the clinker. So it's a clinker ash pickup. So this will influence the composition, and it will influence these phases that we have. The burning characteristics and the flame shape will also be influenced. And basically the air and fuel mixture will also be influenced. So if we look at the fuel ash, you can see that most kiln systems will almost have all the ash will leave as part of the clinker. And the ash composition is very close to the clay because it has a high amount of silica and alumina and calcium. So when firing low-grade coal, the LSF will have to be increased above 100. And coal that we use normally needs to be homogeneous to ensure a constant feed rate and a mineral content that we can predict. So, of course, elements like chlorine, sulfur, and alkali components. So, alkaline components are like sodium and potassium are very important, and they will determine the burning technology. The content of the quartz will have wear and tear on the milling process, at the end. So, when we have the clinker and we need to mill it, it will have an effect. So, of course, today we want to look at alternative fuels. So this alternative energy that we use, other than what we have, which is the coal or the peat that we use, needs to meet the incineration standards used, and it needs to maintain the final product quality. So if we look at the influence of minor elements, so for example, if we have manganese here, it can have an effect on the C4AF, which is the brown millerite. So remember, the C is for the carbon, A is for the aluminate, and F is for the ferrate. The titanium will also influence the brown millerite. Yes, the P2O5 which naturally occurs in limestone and can be beneficial and more detrimental to strength. So every 1% can decrease the C3S by 10%. So we have to control these minor elements very precisely. And most importantly, the industrial waste has a lot of influence because heavy elements like the vanadiums and the zincs, which are transition elements, or even lead, which is a heavier element, can influence these phases that we get in the clinker. So, for example, vanadium can influence the C2S. So the vanadium can come from pet coke, for example, or any alternative coals that we use. If we're burning tires, for example, the tires contain a lot of zinc. And of course, the zinc can influence the C3S content. So these will increase the reactivity of the clinker. And lead, of course, is very volatile at 750 degrees and will also influence the reactivity of the clinker. So we need to really quantify the analytics of the alternative fuels. So if you look at the alternative fuels, here we have a nice example of elephant grass. So this has a very high biomass and can yield a lot of energy for the process. So elephant grass is available in certain parts of the world. For example, Rwanda is one example. It's very fast growing and adaptable as a perennial grass and can be used as a kiln source of combustion. So the pyrolysis heats the grass in the absence of oxygen and can produce, for example, a bio-oil or like a gas or even a biochar, while direct combustion involves burning of the grass directly for the heat. So if you look at some of the examples, the alternative fuel when burned, like elephant grass, will convert to ash, and this composition will have an influence. So if we have other alternative fuels, elements like sulfur and chlorine and alkalis will have an influence. It can also affect the refractory lining of the kiln, so we have to be careful and investigate this. Of course, we have some trace elements, and these can have impacts on the process, like the fan capacity or the quality of the cement or the emissions. Of course, the use of alternative fuels can greatly reduce the CO2 reduction, so this is an important part. and biomass content and emission factors can influence greatly. So we can mitigate the use of fossil fuels, which is like coals, saving a lot of costs and having a cost implication. Yes. So here we can see different categories of alternative fuels. We can get liquid alternative fuels or solid alternative fuels. So liquids can be waste oils like solvents, animal fats, sewage and sludges. So these are all in a liquid form or even like in a suspension with solids. So we need to measure these as well by XRF, which is very easy. Solid fuels can involve pet cokes, or even here you can see tires that can be fed into the process. We can even have animal meal or bone meal, or even dried sewage sludges can be used. We can also use medical waste, but this is very tricky in terms of environmental impacts. So, of course, if we look at refuse-derived fuels, it's called RDF. We can have, for example, paper and pulp and cardboard, things like plastics and packaging, or even wood, for example, or textiles from industry. So any kind of alternative fuels can be used. So this is very beneficial for the environment, because if we can try to use these materials, we basically get rid of this in the kiln. So it's very good for the environment. Yeah. So, of course, alternative fuels can be used not only in the cement industry, but also in coal-fired power plants. Of course, tire-derived fuels can be anything from scrap tires or whole tires, and they can be mixed, or they are always mixed with the coal or other fuels to dilute it, like, for example, with wood or chemical wastes, and can be fed into the kiln or coal power plants, or even into the paper mills. So in the cement industry, we use the tire-derived fuels a lot, and paper and pulp use it around 29%, and electrical utilities use about 25%. So the cement industry is the highest user of tire-derived fuels. So, of course, refuse-derived fuels, for example, municipal waste like industrial waste or commercial waste, consists mainly of components like plastics and paper and recycled plastics, cardboards and wood. And these are also used very often in these different industries. Yeah. Other materials such as glass and metals need to be removed. Like if you have the tires, you have metals, they need to be removed. So here you can see on the conveyor, it's fed into the process, and this needs to be removed. Otherwise, it could be detrimental to the kiln. So you can remove them and sort them mechanically with special equipment. Yeah. So if we look at the tire-derived fuels, it's very important that we have an EPA test program to ensure that we do not have potential emissions that could be detrimental to the environment. But like the conventional fossil fuels have a long combustion, and they can be used in well-maintained combustion devices. So we can get, for example, wet scrubbers for flue gas treatment in the process. So we need to always take care of the environment. We cannot just burn anything. So a lot of strategic planning and investigation needs to be done on the materials before they can be used in the process. So, of course, as you can see, in the cement manufacturing process, we have our manufacturing process has to be optimized in the proper way for quality control. We have the control parameters and the analytical solutions. So in order to optimize the replacement of fossil fuels with alternative fuels, we need to investigate these materials very closely, and yes, make sure that the alternative fuels do not have an impact basically on the reactivity of the clinker. So it's our way of driving the raw material and fuel. The costs need to be driven down so that we have environmental compliance. And in this way, we can produce a greener cement with a lower cost. So we need to control the waste, the fossil fuels that we use in the kiln, to, of course, reduce the CO2 emissions, which is the major driver in the cement industry in the 21st century. So, of course, in order to reduce the clinker factor in cement for the benefit of hydraulic materials, we can use extenders like slag and pozzolana, and we can reduce the input of electrical energy by avoiding to grind the cement to a very low fineness, as required. Yes. So what about the toolbox? So our toolbox needs to involve analytical equipment that can help us to investigate these materials. So, of course, here you can see we can use XRF, which is a main analytical tool to assure proper composition of our materials. So heavy metals and transition metals, due to alternative fuels, need to be tested. And the materials need to be tested at the correct detection limits. So, of course, an XRF is an excellent tool for major, minor, and trace element detection. Microscopy can be used as well, which is an old technique where we can look at the phase sizes, the amount, distribution, and other characteristics that will reveal the information about the clinker history and the kiln temperature profile. Of course, the clinker that's done by microscopy will provide the information about the raw material, the burnability, to improve the clinker grindability, so that we can mitigate any problems that will occur in the production. We also have, for example, an X-ray diffraction instruments that can be used for mineralogical composition for the clinker and any unknown materials that may cause problems in the process, like if we have kiln buildups or ring cyclone chokes. So these instruments are used very often in the cement industry. Thermal analysis is a very well-known technique, also very useful because it can quantify organic emissions from the fuel that we use and the secondary materials that we use in the cement manufacturing process. And we can also investigate cement sulfate forms and cement hydration products. So these instruments are very useful for problem solving. If you have, for example, kiln buildups or finishing mill problems or operational problems. Yes. So if we look now, I will focus on how we can measure the alternative fuels for using wavelength-dispersive XRF. So this is our products that we have at Rigaku. These are all sequential wavelength-dispersive instruments. So we have the Primus series of instruments. We have the Simultex, which is the most powerful system. This is a simultaneous XRF instrument. And we have the benchtop instrument, which is the Super Mini 200. So in all the examples that I am going to show you today, I will be using the Primus 4, which is our standard system. I will not talk too much about the instrument now because I want to talk more about the analysis and the preparation of the alternative fuels. But in short, the ZSX Primus 4 is our 4 kilowatt system. And the advantage of this instrument is, of course, that we have the X-ray tube above our sample. So this is a very nice solution for this, for example, the cement industry or even other industrial customers where they work in very dusty environments and they need to measure, for example, pressed powders, which is the main method that's used for quality control. And of course, the advantage of this is, of course, we have the best sensitivity from having the X-ray tube above, very reproducible sample positioning, and most importantly, we do not have any contamination in our chamber due to an inferior sample that's measured because of maybe a broken pellet, because basically it will not fall on top of the X-ray tube, which is the most expensive part of your instrument. Okay, so let's look a little bit about how the elemental analysis of X-ray fluorescence works. So here you can see the hardware features in an instrument. So we will always have an X-ray source, we will have the collimators, we will have the analyzing crystals, and we will have the detectors. So of course the analyzing crystals in a wavelength dispersive instrument provides the proper separation and resolution of our peaks, which you can see here. So we can measure samples either semi-quantitatively or with a quantification method. So of course the quantification method is very useful if you have calibration standards, and you can measure for quality control using this way. But now we are using alternative fuels, and we want to look at the analytical results from an alternative fuels, and this becomes very complicated because it's not easy to get analytical standards for the setup of a proper quantitative method. So therefore we use what we call our semi-quantitative analysis. Okay, so if we look now at semi-quantitative analysis in the Rigaku software, we call it SQX. And basically this analysis works as follows. So we will prepare the sample, we will get a qualitative scan, and from the qualitative scan and detected elements, we will quantify this using a fundamental parameters method, which has been set up with a sensitivity library from the factory. So if you look now, this is an example of a semi-quantitative analysis. So this is the example of a qualitative scan, and this is the detected lines. So you can see we have L lines, we have K lines, we have alpha and beta lines. And so these lines have been identified, and once they've been identified with a clear peak, then, which is automatically done by the software, these will be measured for the intensity. So each line will be measured with an intensity, and these intensities will be used from the unknown sample, and we will use the sensitivity library to calculate using fundamental parameters what the concentrations of the elements will be. So the sensitivities that we obtain in this library is set up by the factory. So most importantly, I want to show you another method, which is called the scattering FP method. So this is a very useful method in our software to measure alternative fuels. Why? Because alternative fuels are mainly organic. So if you look at waste, like refuse-derived waste, or tires, or municipal waste, or even the elephant grass that I showed you beforehand, these all have a very high organic component. So therefore, we use the scattering FP method. So how does it work? This is a pool that you can see of different materials. So we have metals and oxides, liquids and polymers, sludges, scales, waste oils. And of course, the semi-quantitative method is using the fundamental parameters method. But if we want to measure these materials, then it is easier to use the scattering FP if we have a very high carbon, hydrogen, oxygen, nitrogen component, which is organic. So therefore, we can measure the balance of these materials very successfully using the Compton line. So it's called a scattering FP method. So here you can see, for example, the analysis using the Compton. So this Compton line will have an influence based on the different matrix. So here we have an example of gypsum and kiln feed. So these are natural materials, from the mining process. Kiln feed is a mixture of clay and sand and limestone and bauxite, for example. So those 4 components are part of a kiln feed. And of course, because they have different matrices, they have carbonate portion, they have a crystal water portion, and these portions are picked up by the Compton line. So we can estimate this balance very easily. Here we have another example where we overlaid the Compton line with a polymer and a gypsum. So polymer has a very, very high organic part of the matrix. So therefore we have a much higher Compton line, more intense. So our scattering FP, as you can see, which is an optional part in the software, is very useful for the analysis of these materials like rocks and limestones and plastics, because this will have an influence from the hydrogen, carbon, oxygen, nitrogen portion of the material. Yeah. So if we look now at the analysis of a tire, so of course this is an example of a tire that's been shredded and cut, and we can see we have a very heterogeneous sample. So how do we make the heterogeneous sample into a homogeneous sample? Well, there are different types of equipment that are available to mill the sample using cryogenic milling. And this is exactly what we've done here. So we've shredded this and we've gone to another step, which involves cryogenic milling. So we make the material hard and brittle by treating it with liquid nitrogen, and we are able to then produce this kind of sample, which still looks heterogeneous, but it is completely pulverized. And now we can comfortably make what we call a pressed powder from this. Of course, the pressed powder needs to have a defined density, so we need to have an infinitely thick sample to be able to measure all the elements that you see here. So in this example, you can see that the carbon portion was measured using the fundamental parameters scattering FP method. So this means we measured the Compton line to get the balance of the material, which is in this case from a sample A and B, which is this. We measured it twice and prepared it twice. You can see there are differences because it's heterogeneous. And this material contains minor elements from sodium up to zinc. So as I mentioned, tires contain a lot of zinc, and as we saw earlier, we have the zinc will influence the process. So it's very important that we get a good analysis from this material. So my recommendation to analyze this properly is to make several measurements from this very heterogeneous sample. Yeah. How else can we measure alternative fuels? So here you can see a lot of waste. And on the plant, we have an instrument or a process instrument that can shred the material. And after shredding the material, you can see a big pile of the waste with different colors. So, of course, sampling is very difficult here for the laboratory, but this is not about sampling, but we could do another topic for that. But of course, to try to get a good sample here, is a challenge. Yes. Once we have obtained a good representative sample from this, we can then make an analysis in the laboratory. So, of course, from this pile, we took 5 different samples, large samples, because it's a big stockpile. And the large samples were treated in the same way as I described before. And we prepared the sample 5 times. And of course, as you can see, it's a very heterogeneous sample. And of course, using the scattering FP, once again, to estimate the balance of the material, we have defined the balance here. So the more consistent the definition of the balance, the more consistent the analysis of your results will be here. So this result was done actually on our smaller instrument, which is the Super Mini 200 with a palladium source. So the biggest advantage of the Super Mini in this case is the determination of chloride. Why? Because we have a very good peak to background ratio, because we have no spectral overlap from the rhodium tube, which we can conventionally get on our bigger floor standing instrument. So you can see here at the bottom, we also determined chlorine, but with a rhodium target. And of course, the drawback is we don't get a really nice peak to background ratio in this spectra that you see. So once just highlighting that, of course, a Super Mini can also be very useful, especially for the analysis of chlorine. And chlorine is an important part that we need to measure, because this can also influence our kiln. Yeah, if we have a lot of alkalis, a lot of sulfur, and a lot of chlorine, it can be detrimental to our kiln, because it can cause buildups in our kiln. Yeah. Here's another example, but now we have a traditional coal sample. So of course we need to also measure coal, because the coal will be used in conjunction with the alternative fuels. We cannot use just alternative fuels in the kiln. It has to be accompanied with coal. So of course coal traditionally can be measured with a fusion method, but in this example I showed you how we can ash the coal by using an ISO standard, as you see here. And the ash content can then be measured for the trace elements that we have here. So this ash needs to be prepared in a certain way. And of course, the ash content needs to also be part of the analysis. But the coal ash that I've given here also uses the scattering FP method. And as you can see, we can pick up elements from sodium up to lead. And as I said, it's important for us to measure the trace elements here as well. So once again, we used the scattering FP method, and we combined it also with a comparison of just putting carbon as an input. So you can see from the results, for example, the reference value is 0.029%, for example, on arsenic. Using the scattering FP, we get 0.035%, and using and setting carbon as a balance is 0.017. So you can see 2 kinds of methods can be used for the analysis of trace elements and, of course, the lighter elements. Yeah. Here we have another example using semi-quantitative analysis. This is quite a nice example, because we can use, for example, a certified reference material. And in this case, we used a Geochemical Society of Japan reference material. And of course, the reference material will always come with a certificate of analysis for the major, minor, and trace elements. So we can use and analyze the sample as a loose powder, for example, using our example that you see here with a film. So here you can see the details on how we prepared this. And of course, we can create the analysis that we get as a matching library. So it's like a fingerprinting of our materials. So you can see, for example, if we set it up as a matching library, then we can measure the sample using the matching library, and these are the results that we can get. So you can see the certified values on the top for the major and minor elements, and then at the bottom, the trace elements in ppm. And you can see that the actual results obtained are very close to the certified values using semi-quantitative matching library. So very useful. Okay, here's another example of a refuse-derived fuel using the scattering FP. So you can see, once again, we're using the rhodium K alpha line for the analysis of the balance. So the scattering FP method here yielded a balance of 87.6%. Using the rhodium K alpha Compton line. So as you can see, the results are expressed here as an oxide. And what's very nice from our software is that we get the information about the analyzing depth. So if we are looking, for example, for the zinc in the material, it's very important that the zinc that we measure here has an infinitely thick sample, because the heavier elements, like you can see here, have a deeper penetration into our sample. So we need to have a thick enough sample for the analysis. So this is why our software is so beneficial for getting the correct analytics for our alternative fuels. Here's the next example, which looked like this after cryogenically milling the sample. And after cryogenically milling the sample, we prepared the sample with a wax to make it a nice stable pellet that we can press. And you can see this is what it looks like. Yeah. How do we set up the analysis of the alternative fuels? So it's very easy for us to create a method. So this is the example of the method that we can create. And we can also optimize or make the measuring conditions better by changing certain parameters. For example, we can make fixed angle measurements on certain elements that are important, like, for example, if trace elements are present, then we want to spend longer on the counting of the peak to get a better peak to background ratio. So this is the optimized condition, and we can change this, in a semi-quantitative method. As mentioned, we always need to look at the stability of the measurements, so we can do repeatability measurements here. Just to show you how stable an XRF is, it's all about precision, not about accuracy. So the precision of a result can be shown by basically preparing the sample 20 times and measuring the sample 20 times. So here you can see a table where we average the results of the 20 measurements using the scattering FP. So you can see, for example, we spoke about zinc a lot, so we can look at zinc, and you can see on average we get a value of 0.072% with a very small variation in the repeatability measurements. So this shows that XRF is a very reproducible method and has a very small deviation in the results. Yeah. So once again, showing the precision of the result. Okay, so here I want to talk a little bit and show you a little bit about how you can prepare this kind of sample. So here you can see an example of waste, like municipal waste. So many industries, even the petrochemical industries, can extract oils from here, and they also need to measure these samples. not only in other industries, but here, for example, you can see a lot of different colors and a lot of heterogeneous sample. So, of course, the first thing we need to do is to dry the material at the correct temperature. And then this dried material can be passed through like a cutting mill that you can see here. And then after it's been shredded and cut, we can split the material and then undergo what we call a centrifugal milling, so that we land up with something, a bag that looks like this. So, of course, it looks still very heterogeneous, but we have tried to make it as homogeneous as possible by undergoing the different steps in the preparation. So after we have got a sample, a representative sample from what we had, we can try to split this material again and then try to prepare a pressed powder. Or because it has a very high organic content, we can use what we call a hot press. So this is a press machine, but it has an attachment where we have heating plates, and the heating plates help to not only press but melt the material to be able to get this kind of sample that you see here. So it has a very smooth analytical surface with a nice analytical height, because we need infinite thickness for the analysis of not only the light elements but also the heavy elements. Yeah. Of course, the heating plate will also ensure that we get a very smooth analytical surface. So if we would like to measure sodium in this particular sample, it would be very easy, because we will have no imperfections in this analytical surface. So, of course, the analysis of that material that you saw now is shown here. But this analysis is slightly different in that we measured carbon and hydrogen by another technique, and we put these values as a fixed input into the analysis of the semiquant. So as you can see, this would be the analytical results for that kind of hot pressed plastic, and where we, of course, always need to look at not only the analytical result, but detection limits that we get. So we need to observe and refine the spectra, and of course, always make sure that we have the correct analyzing depth. So please take note, always the heavier elements have a larger analyzing depth, and therefore it's always important that we have this very thick pellet, for the analysis of these heavier elements. Okay, so what about Rigaku's solutions for the cement industry? So, of course, as you can see, we have a very nice portfolio of wavelength dispersive instruments. In particular, the Primus 4 is the most commonly used for quality control. Of course, also the Primus 3 next. But of course, all our spectrometers, as you can see, are norm compliant. So, of course, in the cement industry, we need to ensure that we adhere to the ASTM, the EN methods, and the ISO methods. So all of these instruments are norm compliant with pressed powder and fusion for the instrument specifications that are given in these standards. So the main components that we normally analyze are shown here as oxides, and can be set up very easily for you with calibration standards as mentioned in these norms. So we have a lot of application notes on our website, so please have a look at them so that you can get more details. Okay, so let's talk about some of these international norms. So if we look at the ISO 29581 for fusion, we have many fused bead standards that are available to set up these calibration methods. So one of them is the pre-calibration package that we can offer. And at Rigaku, we call it an oxide fused bead pack. So it's a very wide calibration range that you can see here. But it's not good enough for the analysis of the cement. So therefore, we have other solutions that we can show you because, of course, the cement needs to have a narrower range and not such a wide range. So why do we have the wide range calibration? Well, this is to characterize all our raw materials that we have and the clinker and the cement, of course. Yes. So many different ranges are available, are present in those different materials, and therefore we need the wide range calibration. So with this wide range calibration, you can see the analytical range for all the oxides, ranging from alumina to zirconium, and the accuracy that can be achieved on this analytical method. So more dedicated and more specific calibration sets would involve, for example, the ISO 29581, which is a narrow calibration range, and this would be for the cement, the raw meal, and the clinker. The other one is the raw professional, which would be for the cement industry, the glass industry, the steel industry. And then we get the raw professional, which is a much wider range, which is the oxidic raw materials. So if you are interested, please contact us for more details on the solutions that we can provide. Okay, so if we look at the pressed powder method, we also offer at Rigaku what we call the cement pressed powder calibration method. It's also a pre-calibration method. And of course, this is the example of the analytical range and the accuracy that can be achieved from silica all the way up to the element chlorine. But please note, because of matrix matching, it would be ideal for you to add additional standards onto this calibration to extend it to have the matrix matching. Yeah. So at least 95% of your results should represent the matrix that you have, because of course pressed powder has the drawback in that we need to have matrix matching standards. The other examples of pressed powder calibration sets, not only cement, but we can have slags, clays, limestones, dolomites, sand, gypsum, and bauxite as the pressed powder. So I have shown you now pressed powder and fusion calibration standards that are available, but we can also help you with doing matrix matching calibration. So if you buy a new spectrometer from us, we will work together with you to certify your reference materials, and these references are called secondary standards. So for pressed powder, this is very important, and therefore we can do this for you. Yeah. So the importance of secondary standards is, of course, that we have an in-house certification based on the international reference method. And of course, if you have matrix matched calibrations, your accuracy and precision of your raw materials will be very good with the pressed powder method. So here we have an example of a limestone. And if the limestone quarry has different grades of limestone, we can certify the different grades of the limestone to make a good calibration range. Another advantage about the XRF software at Rigaku is we can not only create an empirical calibration, but also a fundamental parameters calibration. So please contact us for more information about this. We also offer other application and pre-calibration methods, which you can see here. So these are based on fused bead and pressed powder, and they are available on our different instruments that you can see here. Another very useful calibration package is, of course, the GeoTrace pack, which is very important for the analysis of not only the lighter elements, but also trace elements in geological materials. So this is established with 101 certified reference materials. So it's important with your spectrometer to also have a standard operating practice for calibration maintenance. So we can do this for you, and we can set this up automatically with check samples and drift corrections. Drift corrections could be done as global drift corrections or individual drift corrections. The integration of our analytical results can be transferred to LIMS, to any external data transfer like QC, Blend Expert, PrepMaster, PoLab, and of course, most importantly in the cement industry or any industrial customer, is that we can define the user access levels to protect the calibration methods that have been defined and so on. Yeah. In terms of service and support, we have a help desk at Rigaku Europe. And of course, we also offer extensive European dedicated technical and application support. So you can see some examples here. We're very flexible with the service contracts for your requirements. Of course, why should we have an XRF and why Rigaku? So it's very important in any industrial process to have an instrument that's norm compliant. So of course, all our instruments are norm compliant. We are it's a very cost efficient analytical instrument. It's very easy for non-experts. So you don't need to be an XRF expert to use the software. And as you can see, even if we have alternative fuels, we can comfortably measure very difficult matrices and samples, not only with calibration methods, but also our very powerful fundamental parameters, SQX methods. Very reproducible analytical results can be obtained from an XRF. So why the Rigaku XRF? So we didn't tell you too much about Rigaku, but Rigaku is a global leader today in X-ray technology, and we were established in 1952, and we have a full product range from WDXRF and energy dispersive XRFs to even online XRFs. Because we are a Japanese company, we permanently are developing our products, and so we have the Kaizen philosophy. So we are very proud of our XRF equipment that we have available because they are very rugged and reliable industrial units. So the last thing that I wanted to show you and share with you is the sum of the unique advantages of a ZSX Primus 4. As I mentioned, one of the best features here is, of course, the X-ray tube being above the sample. So this minimizes the risk of any breaking pellets on top of your X-ray tube. Additionally, this kind of instrument will be a very robust instrument because the X-ray intensities will not change rapidly because of the X-ray tube above. So it also has the best sensitivity for light element analysis because of automatic pressure control and having the X-ray tube above. And of course, most importantly, the very reproducible positioning of the sample for the analysis. We also have unique crystals like the RX crystals, so they are Rigaku crystals, and they offer a lot of intensity for some elements because they have been designed for the analysis and separation and resolution of specific elements. And lastly, the very thin beryllium window, which is very thin in comparison to others, will offer you at least 40% more intensity for very difficult elements like light elements, which have a low fluorescent yield, like fluorine and sodium and even boron, if you would like to measure this. So yes, please contact us, visit our European Center of Excellence. And yeah, this is our contact details. So I was over the time, I'm sorry, but maybe we could try to do some questions, Niels.
Yeah, Carmen, thank you very, very much for this great webinar. And I received already quite a lot of notifications that the attendees were quite happy and asking a lot of questions. So we can't answer all now live, but we will answer every question via email. Yeah, and just briefly, after the webinar, we will send around a quick survey, and it would help us quite a lot if you take the time and answer the survey to improve our service, our webinars. Yeah, and so let's dive right into the first question. One attendee points out that in the municipal waste sample, the analyzing depth is given with 14 millimeters for a bromine. And the question is, if the finished pellet is only 5 millimeters, are the value for bromine still correct for that element?
Yes, so of course, these very difficult heavy elements are critical. So we need to make sure that our analyzing depth is satisfying our thickness of our pellet. So if your pellet is very thin and it does not satisfy that calculation that's based on that, then please do not trust the result and do not report it because it's not correct. We can try to do other analysis with another line. So, for example, bromine also has like an L line. So we could try to change our method to try not only measure a K line but maybe an L line. And because of the differences in the K and the L lines, we will have a different analyzing depth. So yes.
Okay. And the next question is on matrix matching.
Yes.
How can we do matrix matching for the cement pressed powder for central laboratory?
Okay, so matrix matching of standards is very important and very critical for the pressed powder method. For example, if you have a limestone quarry and you would like to set up a pressed powder calibration, we need to obtain different grades of the limestone in the quarry. So you can look at the color, you can look at the a quick spectral scan to see if you have a variation in the calcium and the silica, for example. And in doing this, you get a good range. And then from the range of standards, we could then certify this not only with XRF reference method, but if you have other methods in your laboratory, you could certify the standards in this way. You can also have certification done by external companies, for example, where they have the ISO accreditation for the certification of secondary standards. Once you have certified your secondary standards, you can combine these together with certified standards to create a successful and good calibration range with a good calibration for limestone for that particular quarry. Yeah.
Okay, thank you. Maybe one last question referring to sample preparation. What would be the preferred method of preparing an alternative fuel? Cryogenic milling or ashing?
So the problem with ashing and alternative fuels is, of course, that you could lose, because it's a burning process, you could lose, for example, some of the lighter elements like chlorine, which you need to know for the process. So the best way to measure an alternative fuels is, once again, to cut it and shred it with a cutting mill. Cryogenically milling and pressing the sample. It would be better because then you retain the entire elemental composition. You don't lose anything. So the problem with ashing is, of course, we could potentially lose any volatile elements from this process. Yeah.
Okay. Thank you. Maybe we have time for one last question.
Yeah.
The question is if we have methods for liquids, which may be liquid at room temperature or liquid at elevated temperatures of 60 to 80 degrees, and
Yes.
if there are reference materials for these kinds of samples.
So it depends on the on the liquid that you want to. There are many reference materials available for fuels like oils, lubricating oils, and so on. But what we could do is we could set up a universal calibration, but in the universal calibration, we can apply what we call a matrix correction. So the matrix correction will compensate for any differences in the oxygen content of the fuel or the hydrogen or the carbon in that fuel. And in so doing, this matrix correction will be able to measure this material that could be a solid at room temperature, but then at elevated temperature, it would be a liquid. So there are many different ways to measure these kinds of materials, yeah? But this would be the best, to do a proper calibration, but then to do the matrix correction, yeah, with the oxygen content.
Okay. Thank you very much. And I would suggest we wrap up the webinar here. The Q&A section is still full of questions. I'm very sorry that we can't answer all here live with you, Carmen, but we will answer every question via email. And please feel free to reach out to us afterwards if you have any further questions.
Thank you very much, Niels, for the great.
Yes, thank you for the great webinar, and thanks everybody for attending and showing interest in the topic of alternative fuels and wavelength dispersive XRF especially.
Thank you. Thank you, everybody.